So, in our last session we completed the recap of our 11th topic, gravitation, right. We have seen the concept of field and potential, which will be helpful for us to understand the concept of field and potential in the upcoming topic like electrostat and magnetism. So, today we are going to start a new topic, electrostat. So, let us start. So, you must have observed that when you rub comb against your hair, then it gets the ability to attract the tiny particles or tiny bits of papers, right. And what about experiencing a tiny shock when you touch someone in dry climate? So, you must observe some shock, right. And it is fascinating to see the thunderstorm. Early culture used to assume this to be a divine force. So, you can see that this is definitely a good display of nature's power and aggression. So, until 1752 people used to see this as divine force, till Benjamin Franklin establishes that the reason of lightning bolt and the reason of tiny shock when we touch someone is same, and the reason was charge. So, charge is nothing but another property of matter like mass. So, in this chapter we will talk about charge. So, in electrostat we will be talking about charge, but with the condition that it is at rest. Here electro means charge and statics means rest. So, this chapter is about charge at rest. So, we will be talking about those cases where our charges will be at rest. So, what basically the charge is? Just now I told it is like another property same as mass. So, matter will have mass, matter will have charge. So, how charge is defined? So, charge is the property associated with the matter by virtue of which it experiences and produces electric and magnetic phenomena. So, this is the definition of charge. Charge is the property associated with the matter due to which it produces and experiences electric and magnetic effect, right. Generally we represent charge by Q. So, like mass, charge is also scalar. Charge is a scalar quantity, and any physical quantity we will measure in some unit, and that SI unit for electric charge is Coulomb. So, charge is one property of the matter like mass. In whole 11th we talk about the mass, now we will talk about the charge under different circumstances. See, charge at rest, then it produces electric field or electrostatic field. When it moves with a constant velocity, along with electric field it also produces magnetic field. So, when charge is at rest we observe electric phenomena and the field around it is called electrostatic field. When charge starts moving, along with that field it also produces the magnetic field, and then we will see later what happens when charge accelerates. So, accelerating charge particle produces electromagnetic wave that we will see later, but for time being our discussion is only for those situations where charge is at rest, electrostatic, right. Now property of charges, like mass, charge will have some property, let us see. So there are basically two types of charges named arbitrarily by Benjamin Franklin as positive and negative. So one charge we consider positive and another charge we consider negative. These are the two names arbitrarily given by Benjamin Franklin. Negative here does not mean that something less, or positive does not mean that something more, or I cannot say that plus 2 Coulomb charge is more than minus 2 Coulomb charge. Here plus and minus sign just indicate that they are two different type of charges, right. So two type of charges, positive and negative. Instead of naming AB or XY, it is named as plus and minus by Benjamin Franklin, right. So this is the first property of charge. Let us see next property. Charge of same sign repel one another and charges of opposite sign attract one another. Similar charge will repel each other and unlike charges will attract each other. That means if I have positive charge or negative charge, these charges when released they will try to fly apart. So this will try to move this way and this will try to move this way when they are released. Similarly negative charge, they will repel each other and when released they will try to fly apart. So like charges repel each other while unlike charges, if I take one positive and another negative, one positive charge, another negative charge, if I release they get attracted. So unlike charges will attract each other, like charges repel each other, unlike charges attract each other. This is the another property of charges. So first property, there are two types of charges. Second property, like charge will repel, unlike charge will attract each other. Now let us see next property. Electric charge is quantized. What do we mean when we use the word quantization? That means the charge on any object, if I take any object and say the charge on the object is Q, we say it is integral multiple of charge on electron. Here n can assume plus minus 1, plus minus 2, plus minus 3, so on. So n can be positive negative 1, positive negative 2, positive negative 3. It cannot assume any value like 1.2 or 1.6. So as it assumes all integer value, we say that charge is quantized and charge on body is an integral multiple of charge on electron. Charge on electron is the least possible charge available in isolation. Here I am not talking about the quarks which will be having charge less than this one, like plus 2e by 3 and minus e by 3, up quark, down quark. I am not talking about all these particles, all these elementary particles, because they do not exist in isolation. So here our focus is only on electron because it can exist in isolation, right. So we are not talking about the quarks here. So charge is quantized, charge on any body is integral multiple of charge on electron. It can be a positive charge, it can be a negative charge, right. So that is why we can have plus or minus 1 or plus or minus 2. So if we give 2 electron to a neutral body, if I give 2 electron to neutral body, then charge on this one will be minus 2e. It will be having excess of 2 electron. If I just remove 2 electron from the neutral body, then it will be having, if I take 2 electron from the body, then it will be having plus 2 E charge. I cannot remove charge less than 1 E from the body. So that is why the least possible value is E. Either it can be plus or minus, that depends on whether I have given the charge or I have taken charge from the body, right. So this is electric charge is quantized. I hope this concept is clear. Now conservation of the charge in an isolated system. See, if I take two bodies, one is having plus 2 microcoulomb charge and another body having plus 3 microcoulomb charge, and they are conductor. If I connect them directly or by some conducting wire, if I just join them, then few electron will move from one body to another body, right. And finally what happens, this system, say this body is having charge q1 and this body is having charge q2. As I join them by insulated handle, I connect this by insulating handle, I connect this by insulating handle, and just I touch these two. That means there cannot be any outflow from this system. So I am considering this as system, and there is no outflow from the system, charge will just flow from one body to another body. This system is called isolated system. So according to conservation of charge, for an isolated system, the total charge on the system remains same. That means after joining them, q1 plus q2 must be equal to this 2 plus 3 microcoulomb. That means you cannot create net charge or you cannot destroy net charge. You can create charge, you can destroy charge, but you cannot create net charge or you cannot destroy net charge. In pair production and annihilation process, we get and we destroy charges, but the net charge on the system remains same, right. So net charge cannot be produced or cannot be destroyed, or I can say on an isolated system the net charge remains same. So I hope these property of electric charge is clear. Let us move to other properties. Electric charge is a relativistic invariant. What does that mean? See, unlike mass, if electron moves with a velocity close to the speed of light, the charge on the electron remains same. This is called relativistic invariant. So from special relativity, we know that mass is given by m naught divided by under root 1 minus velocity divided by c whole square. So, mass, energy, these all are relativistic variant. So, these all are similarly energy I can write in terms of, or I can modify this term according to the Lorentz factor, right. So, energy and mass, they are relativistic variant, but no matter whatever be the velocity of electron, the charge on electron will remain same. This property is called relativistic invariant. So, charge on electron is one of the invariant of physics, right, unlike mass. Now, let us move to next property. See, now basically we divide object in two ways. We say whether they conduct or they do not conduct. So, what are conductors? Conductors are material in which electron can freely move. Electron can freely move, those materials are called conductor, while insulators are the material where electrons hardly flow. Similarly, we have another type of material which is called semiconductor, that we will talk later, but for time being, where there is no possibility of movement of charge from one body to another body, when body is not allowing charge to flow, we put them in the category of insulator, and when they able to move their charge or they can accept the charge, we put them in the category of conductor, right. Now, let us move to next one. The method of charging, how we charge the body. We are talking about the charge, how we can charge a body. So, normally in our first slide I said कि when you rub comb against your ear, then comb gets the ability to attract the tiny bit of papers, right. So, by rubbing you can charge. So, when you rub comb against your ear, then comb gets the charge, right. So, first thing, or by first rubbing we can make the body charge. For example, when you rub glass rod against silk, then silk get negatively charged while rod get positively charged. So, rod gets positively charged and silk gets negatively charged. The body, one body is getting positively charged and another body is getting negatively charged is only because of the difference of electron affinity of one of the body. If electron affinity of one of the body is more, then it will get the charge. So, it is a matter of electron affinity that which body will get positively charged, which body will get negatively charged. So, by rubbing we can charge body, right. Now, next one, by contact. Just now I gave the example that one body or one conductor carrying plus 2 microcoulomb charge and another one carrying plus 3 microcoulomb charge. When you touch, then electron from one body start moving towards another body, and the process keep happening till the potential of both body will become same. Again they will be under electrostatic condition, and finally this body will have Q1 charge and Q2 charge, right. So, I can charge body by just touching. For example, if our second body is not having any charge, assume that this is a conductor which was not having any charge and we put conductor having charge in contact with the first one, then the first one receives the charge from second one. The first one start receiving the charge from second one until again electrostatic condition is achieved. So, we can charge a body by touching another conductor to the body. So by contact we can charge a body, right. So by rubbing, by touching, by induction. So in case of induction we don't touch first conductor to second conductor. By induction we can charge the another object. So without touching we can charge another object. The process of charging by induction we will see later, but for time being even without touching we can charge this body, and that process is called conduction, right. Later we will talk about this one when we will talk about conductors. Now charge by thermoionic emission. So if you keep heating the body, electrons start coming out from the body, and that process is called thermoionic emission. So you can also charge the body by just heating it up. So as electron keep going out of the body, body will get positively charged. So this is one way of charging. Another way, photoelectric effect. When a metallic substance is exposed to light or radiation of frequency larger than critical value, then what we observe that electron start coming out from that metallic substance. This is called photoelectric effect. So you keep body in radiation, if frequency is larger than a particular value or a critical value, then we observe the emission of electron, that is called photoelectric effect. So by this way we can charge the body. Another one, charging by field. So if you keep the body in very high intensive field, so highly intensive field, if we keep a body, then inside the body electron start experiencing the force. If force is large enough to make the electron leave the conductor, or if force is large enough to make electron to overcome all the forces due to the body, then electron start coming out and body start becoming positively charged. So this is another way of charging the body. So by rubbing we can charge the body, by touching we can charge the body, by thermoionic emission we can charge the body, by photoelectric effect we can charge the body, and by field emission we can charge the body. So these are the way by which we can charge the body, and by induction how to charge the body we will see later, but for time being you can keep that in mind. By induction we can also charge the body, right. Now let us see one example. So if I take a piece of copper of mass 3.11 gram, so in the piece of copper or inside atom, if you see, the number of electron and the number of proton will be same, and atom will be electrically neutral. So if you are taking a piece of copper which is electrically neutral, it will be having same number of electron and same number of proton. Now it says ki as it is being electrically neutral, it contains equal number of positive and negative charges, right. So what is the magnitude of these equal charges? So I want to find out what is the total amount of positive charge we have and what is the total amount of negative charge we have. So how to get, say, positive charge or negative charge? If I can find out how many atoms are there in this mass, how many atoms are there in this mass, right. after getting number of atom in this mass, I can multiply, as each atom will be having these many proton, I will get the number of proton, and every proton will have charge 1.6 into 10 to the power minus 19 Coulomb. If I multiply to that quantity, I will get the total charge, total positive charge on the body. That means what I can do, first I can find number of mole, that is mass by molar mass. In 1 mole, how many atoms are there, that we know. So, in these many mole, number of atoms will be, if we multiply to Avogadro number, then we will get number of atom, right. So, mass you have, molar mass you know, if you divide you will get the number of mole, and if you multiply to Avogadro number you will get the number of atom. Now, number of proton or number of electron, say for example I want to find out number of electron. So, how many number of electrons are there? These many atoms will be there, these many atoms will be there, and every atom will have these many electrons. So, I will multiply this to 29. And what is the total charge associated? For total charge, what I can do, I can multiply this 29 into n into charge on electron, I will get the total negative charge. So, see, so n is equal to Na, Avogadro number, m by capital M, you know molar mass of copper, this is 63.5 gram per mole. If I divide, then I will get 2.95 into 10 to the power 22 atoms. These many atom, every atom will be having 29 electrons. So, these many atom, if I multiply to 29, I will get the number of electron, and if then I multiply to the charge on electron, then I will get the total charge, and that comes 1.37 into 10 to the power 5 Coulomb, right. So, I hope this point is clear, quantization is clear. Q is equal to, this is, let us write n into E, right, get the number, multiply to the charge on electron, then you will get total charge on the body. I hope this example is clear. Now, let us move. So, if two similar charges repel each other and unlike charge attract each other, then they must be generating some kind of force, right. It was Coulomb who provided the relation between that force of interaction, and according to Coulomb, the electrical force of interaction between two charges at rest is directly proportional to product of their charges and inversely proportional to square of separation between them. So, let us first see the statement. The electrostatic force of interaction, it might be attraction, it might be repulsion, depending on whether we have similar charges or we have like charges or we have unlike charges, between 2-point electrostatic charge at rest is directly proportional to product of charges and inversely proportional to the square of separation between them, and that force acts along the line joining. During revision of gravitation, I told you when force acts along line joining, then it is called central force. That means Coulomb's force is central force. This is also following inverse square law. This is also following inverse square law. This is central force, right. So, Coulomb was the first one to provide the magnitude of the interaction between 2-point charges. So, if I write this in mathematical form, interaction between two charges in mathematical form, then the force of interaction is given by product of magnitude of their charges and inversely proportional to square of separation between them, and this is proportionality constant 1 upon 4 pi epsilon naught, right. Now, what is this? This is called epsilon naught, and the value comes 8.85 into 10 to the power minus 22, unit is Coulomb square, Newton power minus 1 meter square, right. If you substitute this value here, if you substitute epsilon naught here, then this value comes 9 into 10 to the power 9. If you substitute this value here, then this whole value become 9 into 10 to the power 9. So, better you remember the whole value of this expression 9 into 10 to the power 9. This epsilon naught is called permittivity of free space. Later we will see what is the meaning of that when we will be talking about dielectric, right. So, if two charges are kept in vacuum, the force of interaction is given by this expression. If both the charges are positive, for example, this is positive and this one is positive, then this force of interaction from the property of charge is repulsive. So, the force will always along the line joining, if they are similar charges or like charges, it will be away. If I make another charge negative, so let this be negative charge, so this one I have taken positive, this one is negative. So, the force of interaction, here I am talking about electrostatic force of interaction. So, force of interaction between them will be along the line joining towards. So, they will attract each other with this force. According to Newton's third law, whatever force this exerts on this one, same force this will exert on this one in magnitude, direction has to be opposite, right. So, force of interaction between two charges placed in vacuum is given by this one 1 upon 4 pi epsilon naught q1 q2 upon r square. It might be attractive in nature, it might be repulsive in nature, that depends on the nature of charges, whether they are like or unlike. I hope this point is clear. Now, what if instead of vacuum, this is permittivity of free space, vacuum. Instead of vacuum, if I place them in some medium, isotopic medium. So, property of medium in every direction is same. If I place these two charged particles in some medium, then the force of interaction between them will remain same, but it is the net force between them which changes. So, if I ask, I place the whole arrangement in water or some other substance, then what would be the force of interaction? So, the magnitude of force of interaction between them will remain same, that is not going to change. Again we have the same formula, but if I ask what is the net force changes. So, let us see. So, two particles I am placing in medium, right. Its permittivity of free space was represented by epsilon naught. So, I am calling permittivity of space as epsilon, right. Now, if I ask what is the force of interaction between these two, electrostatic force of interaction between these two is still same. So, force on 1 by 2 irrespective of what is the medium, 1 upon 4 pi epsilon naught q1 q2 divided by r square. But if I ask what is the net force on this one, so what happens, this was either attracting or repelling the another particle, Now when you place a medium, dielectric medium, the charges in the medium start exerting force on this particle. So the net force experienced by this particle will be due to the presence of another charge and the presence of the charges in the medium. So the net force gets modified. So if I talk about the net force, so here I am talking about net force, net. So the force of interaction is still same. If I am assuming this is plus q1, this is plus q2, I ask what is the force of interaction, you will still say this is the force on 1 by 2 and this is the force on 2 by 1. Force on 1 by 2, force on 2 by 1. If I am considering plus, they will be along the line joining away. Still they have the same magnitude, right? But what happened that because of the medium, another force came into picture. So another force, medium also exerts or start exerting force. Force exerted by medium. Let me write it again. So as medium also exert force, then the net force we are talking about, that is F12 minus, because I have already considered the direction, F12 minus F medium using this relation you can also find out the force exerted by medium on this particle, right. Now let us get back to the net force. I hope this point is clear. No matter whatever be the medium these particles are, if I just ask what is the force of interaction between the particles, that is not going to change. It is the net force which gets affected due to the charges of the medium. So medium also start exerting force and the net force particle experiences now is given by 1 upon 4 pi epsilon naught. This is called relative permittivity. ER is relative permittivity. How we write relative permittivity? So relative permittivity is permittivity of the medium divided by permittivity of free space. That is also called dielectric constant. This is also called relative permittivity, is also called dielectric constant. So instead of writing this one ER, I can also write this expression as 1 upon 4 pi epsilon naught q1 q2 r square k. So this can also be written as 1 upon 4 pi epsilon naught k in terms of dielectric constant q1 q2 divided by r square, right. What's the application of dielectric constant and all we will see later, but for time being, if it is or two charged particles are placed in a medium of dielectric constant k, then net force experienced by any of the particle is given by 1 upon 4 pi epsilon naught k q1 q2 upon r square, right. So this is dielectric constant or relative permittivity, and epsilon naught is called epsilon is called absolute electric permittivity of the medium. So I can write K or I can write E here, right. So when particles are in vacuum, what happens we know, when particles are in medium, what happens we know, right. So I hope the formula is clear. Now let us move to next slide. So most frequently we will be using Coulomb's law for the situation where charge is distributed in space. For all such cases it is better to write everything in vector form. So let us see how to write Coulomb's law in vector form. let us consider two positive charges Q1 and Q2, Q1 and Q2 plus Q1 plus Q2, right, and this is the force on 2 by 1 and this is the force on 1 by 2 along the line joining away, right. If I want to write this force in vector form, the requirement is this force in vector form. So, I want to write force on 2 by 1 in vector form. I just need the magnitude that we have just discussed and then I need direction, right. To write in vector form I require magnitude and direction. Now, you can see the direction of the force is along the direction of position vector of second particle with respect to first one. So, with respect to first one, the position vector of second one is r position vector of second one with respect to first one. So, in this direction I require unit vector. So, that unit vector can also be written as r21 cap. So, this direction is same as the direction of r21 cap. So, this can also be written as F21 vector magnitude and R21 cap, and this one is nothing but 1 upon 4 pi epsilon naught Q1 Q2 divided by R square. Okay, let us see. Now, the force on second one by first one is 1 upon 4 pi epsilon naught magnitude of this one and then is direction, right. What if another particle is negative? The direction of force will be reverse. If direction of force is reverse, then what we can do for all such situation, here as this is written in vector form, then we will write these charges with sign, automatically direction will come. So, here Q1 Q2 are with sign. So, remember the sequence, here I am writing 2 1, here also I am writing 2 1. You need not to alter the direction here, just substitute the sign here, force will automatically get reverse. I hope you are understanding. Let me draw it here. This is Q1 and this is Q2. For time being I am assuming this to be positive and this to be negative, right. Now, force, electrostatic force will be attractive in nature, it will be like this. And you can see the position vector right now in this direction, position of 2 with respect to 1 is in this direction. So, if I substitute this charge with sign, automatically the direction of this force will get reverse. So, better if we write in vector form with the same sequence 2 1, 2 1 here and these charges with sign, then automatically this will come in vector form, right. Or else you can see the nature of the charges, according to that force will be along the line joining away or force will be along the line joining towards, right. I hope this vector form is clear. So, when particles are distributed over plane, particles are distributed in 3 dimension and we want to find out the net force on one of the particle, then we can write everything in vector form and we can vectorially add, right, because force is a vector quantity, we need to add them vectorially. So, better you write everything in vector form, then it will be easy for us to add, right. Now, let us see one example. So, I have taken two charges, 2 point charges Q1 Q2, right. Let us say this is Q1 and this is Q2, right, both are positive. So, I am taking both the charges positive and I just want to place one more particle so that all three will be in equilibrium. So, one thing is sure that if I place charge somewhere here, another charge somewhere here, then this will be exerting force on this one along the line joining, and this one will be exerting force on this one along the line joining. These two forces cannot balance each other unless until they act on the same line. So, I need to place this particle on the line joining these two particles, then only force can come in opposite direction, and then only resultant can be 0. So, from this analysis at least we got idea ki where to place the particle, right. So, both are positive. If I place one charge here, right, I do not know distance and all, I will call this distance to something, okay, let us call this distance as d or r. So, q1 and q2 are at distance r, and we want to place a charge q in such a way so that all charges are in equilibrium. So, this is in equilibrium, this one in equilibrium, and this one will come in equilibrium, right. So, as both are positive, this will be producing, or this will be having force in this direction, and this is having force in this direction. They may cancel each other at some point between these two charges. That is why I have kept the particle there. If I keep the particle somewhere here, then you can see this is positive, and this being positive, this will exert force in this direction, and this will also exert force in the same direction. Now, particle cannot be in equilibrium. If you think, if we place negative charge particle, let us take negative charge particle, right. Instead of positive charge particle, let us keep some negative charge particle there. So, if I place minus q here, then you can see this will attract this particle, force will be along the line joining towards, and this will also attract the particle, force will be along the line joining towards. Again, both the forces are in same direction, they cannot cancel each other at the point this side. By the same logic, I can say that they cannot cancel each other at any point this side, right. So, the only option left is placing the charge particle in between, right. Okay. So, I place it here. Now, again see the free body diagram of any one of the particle except q. This q will exert force on q1 this way along the line joining away. I am drawing free body diagram of this. So, forces by all other particle on this one, that is free body diagram of q1. Similarly, this being positive will push it away. So, you can see both the forces are coming in the same direction. Here these two are providing force in opposite direction, they can cancel each other, right, even if this is positive. But in that situation this cannot be in equilibrium. So, what we can do, instead of placing positive charge here, if I place negative charge here, if I place negative charge here, then force by this one on this one will be in this direction, and force by this one on this one will be in this direction, they may cancel each other. Now, for this situation, look at this one, this q1 will attract q and this q2 will attract q, they can cancel each other. So, minus q can be in equilibrium, this q1 can be in equilibrium. Similarly, this minus q will attract this one, while this plus q capital Q1 it will repel this one, these two can cancel each other. Now every element of the system can be in equilibrium, only thing we require is where to place the particle and what should be the magnitude, right, that is the question. I hope question is clear, and how we got the location where to place the particle, this is also clear, logic is also clear, right. Now let us solve the problem. So we are placing negative charge particle, and where we do not know, let this be x, okay. So this remaining will be r minus x. The force of interaction between these two, we know from the principle of superposition that the force of interaction between two particles remains unaffected by the presence of another, that we have seen in gravitation, that force of interaction between two masses is independent of presence of any other mass. Same logic, principle of superposition we are using, so the force of interaction between these two is independent of presence of this one. Similarly, force of interaction between these two will be independent of presence of this one. So we can safely write the force in this situation also, that the force is given by Q1. Now I am just writing the magnitude because direction I have already considered, this will exert force in this direction and this will exert force in this direction, right. So both must be equal, I am just equating the magnitude, I am not writing in vector form, right, because situation is simple, directly I know the direction, I can directly write. So Q1 Q 1 upon 4 pi epsilon naught. One more thing, instead of every time writing 1 upon 4 pi epsilon naught Q1 Q2 divided by r square, from now on we will write this as some constant. You can write C, A, B, whatever you want. Let us write as K, Q1 Q2 upon r square. Do remember that we added one K here, that was dielectric constant. Here I am calling this as K, and that too small k, not capital K. So do not get confused between this capital K and this small k. This small k stands for 1 upon 4 pi epsilon naught, whose value is 9 into 10 to the power 9, and dielectric constant must be written here, right. So I hope this k and this k is clear, they are different. So from now on I will be using directly this format, right, this format. And you can write 1 upon 4 pi epsilon naught also, just to avoid writing more number of term, I am considering this as some constant, right. See, so this force will be equal to K times Q1 Q divided by r square, and this force on Q by Q2 is K Q2 Q divided by r minus x whole square, right. So from here you can see that this K, Q, they all will get cancel out, and we can simplify this one, right. So we can simplify this one and we will get the value of x from here. After simplification you can find out the value of x. Now after getting the value of x, we can also find out what should be the magnitude of charge. Sign we got by logic, position we got by expression. Now we want to calculate the magnitude of charge. So when I am considering free body diagram of this one, this q and q gets cancelled out. That means to get small q if I consider the free body diagram of this one, say this capital Q2 will exert force on Q1 line joining away because both are positive, right, and this will attract this one in this direction. So, if this is in equilibrium, these two forces must be equal. So, next equation I can write is K Q1 Q2 divided by separation is R square. This magnitude of force must be equal to this magnitude of force, that is K Q1 Q divided by x square. So, after getting the value of x, when you substitute in this equation, then you can find out the value of Q2. So, I hope now you can simplify, you understood the concept. After simplification you will get this, x is equal to under root Q1 divided by under root Q1 plus Q2 into R, and Q as it is coming negative, minus sign is there, Q1 Q2 in bracket under root Q1 plus Q2 whole square. I hope procedure is clear. Let us see one example based on the same concept. So, one more point, see under the action of only Coulombian force, the system can never be in stable equilibrium. What is stable equilibrium? What is unstable equilibrium? Let us understand that. So, if I take two similar charges, we are going to understand the meaning of stable equilibrium, then I will come to this statement again, stable equilibrium, right. So, I am keeping two charges fixed, so this charge, they are fixed, and at the middle, if I take some charge plus q, right, exactly at the middle I have taken plus q charge, right. So, they are in space in air. So, this is fixed, this one is fixed, another charge in positive charges at the middle, right. So, right now the forces by this one and this one, they are getting balanced because these distances are same, charges are same, this is balanced, it is an equilibrium, right. If I displace this charge little along y direction, so I displace the middle one in y direction. So, if I displace this one in y direction somewhere here, then this start exerting force along the line joining in this direction, and this start exerting force along the line joining in this direction, right. So, one force is coming in this direction, another force is coming in this direction, their horizontal will get cancelled out, vertical will get added. As vertical will get added, when you release this particle, this will start moving in this direction. That means for this particular point, this in this direction, it is unstable equilibrium because it has not got any tendency to get back to its initial point. So, when you release, it goes in the same direction, it has not it does not have any tendency to get back, right. So, for the situation where particle is in equilibrium, and if you disturb the equilibrium, particle is having tendency to get back to the point, that is called stable equilibrium, and when particle is not having any tendency to get back, it is called unstable equilibrium. So, same position become stable equilibrium when you displace particle in x direction. Let us see. So, I will erase all this, you simplify, you will get these two, value of x and the magnitude of q, right. Now I am explaining what's the meaning of stable and what's the meaning of unstable equilibrium. So you must have learned all these terms in your 11th standard work energy topic, right. Here I am explaining it again in terms of electrostatic, right. So what I said, say what I said, if you displace this particle along y direction, it is kept exactly at middle, right, exactly at middle, forces are balancing, forces are getting balanced. Now when you displace this particle in this direction, as the force coming from this one this way, force coming from this one this way, this will be, this position in this direction will be unstable equilibrium. If I take minus q charge instead of plus q charge, if I take minus q charge and I displace it in y direction, now look at this one. If I take negative charge, then force will be attractive in nature, force will be exerted by this one along the line joining, force will be exerted by this one along the line joining. So when you displace the middle one up, the forces will be like this and their resultant will be in y direction towards the initial position. So when you pull it up and release, it has got the tendency to get back. So for negative charge, this position in this direction is a stable equilibrium, but for positive charge, this position in this direction is unstable equilibrium, right. Now instead of displacing in y direction, if I displace in x direction, let us take positive charge first, right. So this is plus q and from this location I displace it this way. Now this is q, q and I displace along x direction, either in this direction or this direction. I have taken plus small q charge. Now when it was here, forces were getting balanced. When I displace it, now it is near to this charge, it will experience more force away, and as it is at the larger distance as compared to this one, this will exert lesser force. That means when I displace this particle in this direction, net force start coming towards the initial equilibrium position. So resultant of this force and this force now in this direction, and it has got ability to get back to the initial equilibrium point. So for plus q, this direction is a stable equilibrium. For plus q, this direction is unstable equilibrium. I will write it here. So this direction, if you displace plus q, this will be unstable. And if you displace it this way, if you displace in this direction, this is stable equilibrium. And if I take negative charge here, then this becomes stable equilibrium, because when you displace the charge it will have tendency to get back, while this location for this direction, if I take negative charge, then this will become unstable equilibrium. So basically there are three types of equilibrium: stable, unstable and the neutral equilibrium, right. So we have discussed stable and unstable equilibrium. The statement says that under the action of Coulombian force, only Coulombian force alone, system cannot be in stable equilibrium. That means right now you have calculated the position of this third charge particle for which the whole system, that means every element of the system remains in equilibrium. But if you slightly disturb the system, if I just move this way or move this way, the whole system won't have any tendency to get back. So our system is unstable system. If there are some other type of forces like gravitational force is there or some external force is there, then under the action of all the forces the system can be in equilibrium. I may have force here and I am displacing the particle, then I might be getting stable equilibrium, right. But if only Coulombian forces are acting, then system cannot be in stable equilibrium. This point is clear. Now let us see next example. So same as the previous one, here I have taken one negative charge to make you analyze how to decide where to keep the particle, right. So I want to place a charge q so that the entire system is in equilibrium, right. Which type of equilibrium it will be? Just now we have discussed, it will be always unstable equilibrium, right. Now let us get back to the problem. If I place charge here, plus charge, right. If I place plus charge here, then this though will repel and this will attract. Both the forces are in same direction. So nowhere between these two charged particle forces are in opposite direction. That means equilibrium for plus q does not exist between these two charges, right, because force will be in same direction. Now if I place charge somewhere here, plus q, lesser charge at lesser distance will exert force, and that might be equal to force exerted by this larger charge at the larger distance. So it is possible that these two forces will cancel each other and plus q can be in equilibrium this side, right. What about the position this side? So we ruled out any location here, and just saw that for any point this side it is possible to have equilibrium for plus q. Now I am asking, what about the points this side? If I draw diagram again, larger charge will exert larger force, smaller charge at far away point will exert smaller force. As you can see that this smaller one will never be able to counterbalance this larger one. That means on this side there won't exist any point which will make the whole system in equilibrium. So, only option left is placing the charge here. I hope reasoning is clear. Now, let us start solving problem. So, from our logic we figured out that charge must be kept somewhere here plus q, right. Let it is at distance x, okay, and the force exerted by this one in this direction, force exerted by plus 1 Coulomb will be in this direction, and force exerted by this one will be in this direction, right. Let us see the free body diagram of any other charged particle to decide the sign of this charge, right. Now, this will attract this one, this plus q will attract this negative charge, and this charge will repel this charge. This can be in equilibrium, no issue. Similarly, this will get attracted by minus 4c, and this will get repelled by this one. So, both are coming in opposite direction, right. Now, if I make this charged particle negative, then this will attract this one in this direction, and this one will attract this one in this direction, okay, and this negative charge will repel this one in this direction, and this positive charge will attract this negative charge in this direction. So, this can be in equilibrium, this can be in equilibrium, and this can be in equilibrium, all can be in equilibrium, right. So, we have to take a negative charge on this side of plus 1 Coulomb. Now, we want to find out magnitude. Let us first take this charge, so that we will get the value of x, right. So, force exerted by this one on this one, this is 1, I am writing k 1 Coulomb into q divided by x square will be equal to force exerted by this one on this one over, now force exerted by this one on this one, that will be k plus 4c q divided by 1 plus x whole square. Now, you can see that this k and q, this k q will get cancelled out, and if I simplify, then I will get x divided by 1 plus x whole square, right. That is coming 1 by 4. That means x by 1 plus x is coming 1 by 2, and if I simplify, I can see 2x here, 2x is equal to 1 plus x, that means x is equal to 1 we are getting, right. So, after solving I will get x is equal to 1, right. Now, let us find out q also. So, to find out the magnitude of this charge, I can consider the free body diagram of this charge, right. So, I am writing, or let us write it here. I am drawing free body diagram of this one. This will attract this one. This is q into 1 k divided by x square is equal to. Now force of interaction between these two, that is k 1 into 4 divided by 1 square. This k will get cancelled out, and we can substitute the value of x over here, right. So drawing free body diagram of this one, I can find out the value of this charge, right. Now if you simplify, then what you will get? Magnitude you have already calculated, sorry, sign you have already decided, sign is minus. If you substitute x is equal to 1 over here, this is 1 1, q is equal to 4, that means here you are getting only magnitude, sign you have already decided, that is minus q, and position x is equal to 1 meter, x is equal to 1 meter from this side of 1 Coulomb charge, right. Now let us see another example. So instead of taking all the charges on the line, now I am taking charges on a plane. It can be in 3 dimension also, right. So I am taking charges on a plane. Let's take this example. Find q for equilibrium of the point charges, right. So what's the value of q? To have equilibrium of these charges, you can see that there is no issue of stability of plus q, right, because this one will exert force along the line joining this way. Similarly, this one will exert force on this one along the line joining this way. These two will cancel each other. Same way, this small q will exert force on q along the line joining away. This will exert force on this one along the line joining away. These two will also cancel. So there is no problem of equilibrium with q. So this q will be in equilibrium, but this might not be in equilibrium for all the values of capital Q. Let us find out that if for a particular value of Q, this small q is in equilibrium, or for all the value of Q, this will be in equilibrium. Now you can see, now I will draw the free body diagram of this small q. This q will exert force like this. This q will experience force due to this one this way, and this q I have taken that charge positive. So if this is positive, force will be along the line joining this way between these two, or on this one by this one. Similarly, force by this one on this one along the line joining away, repulsive force. Now force by this positive charge on this charge will be in this direction. Now look at the free body diagram, all the forces are coming this way. So if it is in equilibrium, this must exert force equal to the resultant of all three in opposite direction. That means that black one or capital Q, let me draw by vector with black. Okay. Now I hope it is clear कि this force is on Q by this capital Q. they must get balance for it to be in equilibrium. This angle is 45, this angle is 45. Separately, if I draw diagram, let us call F, same distance here and here, forces will be same, as distance here is different, let us call it F dash, and I will call this as F double dash, right. So, you can see that this force will have two components, one in this direction, that is cos 45, another in this direction, that will be sin 45. So, this can be divided, this force can be divided in two directions, this way and this way. I am writing sin 45 this along the angle cos, perpendicular to that sin 45 1 by root 2, I am directly writing by root 2, this will be f by root 2, this component in this direction will be f by root 2. Similarly, I can resolve this force in this direction, that is f by root 2, and in this direction, that is f by root 2. And this one is f double dash. As you can see from diagram, these two will cancel each other, these all will get added, and that must be equal to this f double dash, right. So, what I can write, f double dash must be equal to f dash plus f by root 2, that is 2 times f by root 2, and f dash, this force of electrostatic force of interaction between q, small q, and this q, that is k q square divided by root 2, if I assume the separation to be a, charges are placed at the vertex of square, right. So, root 2a whole square plus 2 times f, what is f? What is this force? Separation is now a. So, q square divided by a square, and double dash is what? Double dash force on this one by this one, right. So, k q divided by the separation between them, this total distance will be a root 2 from here to here, this distance is a root 2, and half of that will be a by root 2, half of that will be a by root 2. So, I can write a by root 2 here. This k get cancel out, even a square will get cancel out, you can rearrange all these terms, and when you simplify, then you will get q is equal to minus small q 2 under root 2 plus 1 divided by 4. That means, for this particular value of capital Q, this system will be in equilibrium. What type of equilibrium? We have already discussed, unstable equilibrium, right. So, I hope application of Coulomb's law is clear, and we have already seen that how to write the force in vector form. So, I suggest you to go through what we have discussed today from your textbook, and then some more point will get clear. If you have any doubt, you can post those doubts and I will try to clear those doubts. So, this is it for today's session. Tomorrow we will talk about the other application of this force, Coulomb's force. Thanks for watching.